Again, welcome to Mathematical Structure for Computer Science, CS 113 class at Pace University, also known as Discrete Mathematics. In these lectures, we're going to discuss about the basic concept of sets. So our main objective is to go through the definition of sets, describing sets, using the roster method, and also the set builder notation. Also, we're going to discuss about some important sets in mathematics, empty set and also universal set, subset and set equality, and cardinality of sets. And also we discuss what is a tuples and also Cartesian product. So here we start with a set, and here we say sets are one of the basic building blocks for the types of objects considered in discrete mathematics. It's very important for counting, and also programming language have set operations. Again, set also is a very important topic in computer science, especially in data structure. Data structure course teaches how data is organized in different ways for a program to access the data. So for example, in data structure, we have something we call the stack or queue. And the difference between this stack queue is how the data is again organized, how we access the data. For example, in a stack, we can again push data from the top to the stack. And if we want to remove data or access the data, we have to access it from the top of the stack, which means in stack data structure, the entry and also the exit of data is only one place. A queue, we have, queue is like a normal line. We have front of the queue and then back of the queue. So when I want to insert an item, I will insert it through the back of the queue. When I want to remove an item, I will remove it from the front of the queue. So we can see the difference between stack and queue data structures. The same concept, also set, is used in data, is actually, I would say it's a data structure. Set is a different type of data structure, which teaches how data is organized and how we can access the data also. So set is very, very important in computer science field. Here, the set theory also is an important branch of mathematics. Many different types of axioms have been used to develop set theory. And here we are not concerned with the formal set of axioms for set theory. Instead, we will use what is called again naive set theory. So what's the definition of a set? We say a set is an unordered collection of objects. So how the objects are arranged, it doesn't matter whether it's assembly order, unordered, it doesn't matter. So a set is an unordered collection of objects. Also, duplicate is not important. We will see an example soon. So example here said a student in this class can be a set. Let's say the set name will be class, and the objects inside the set will be called students. Also, the chairs in this room can be an example of a set. And normally we say the objects in a set are called the elements, or they are the members of a set. So in this case, if our set name is class, and the elements in a set can be students, which we also refer as an object or a member of a set class is students. Now the notation here we say the lowercase a belongs to uppercase A. Always the lower cases will be the elements of the set, and then the uppercase will be the name of the set. So we can read this as lowercase a, that is the element A belongs to set uppercase A. Or we can say it's a member of uppercase A. So this notation again means lowercase a are elements that belongs, or they are a member of uppercase A set. Now, if A is not a member, of set A, which is uppercase A, we can write it as, again, the E with a slash. So this means the element, or I'll say the lowercase a, which is an element, does not belong or is not a member of uppercase A set. So here we're going to describe a set using the roster method. So here we have S equal to, we have a curly brace, uppercase A, B, C, D, then we cross it. So what this means is we have a set A, and a set A consists of element, a set S. We have a set S. A set S consists of element lowercase a, b, c, d. So the lowercase a, b, c, d will be an element or the members of set S. Again, the order is not important. So we can say here we have S equal to lowercase a, b, c, d. We can also say it's the same as b, c, a, d. So set S, uppercase S, its element can be A, B, C, D, or B, C, A, D. They are the same. Here we are talking about how they are ordered. Also, the uniqueness repetition is not really important. So for example, I may have a set S again. The members are A, B, C, D, or the members are A, B, C, D. We can see that we have two C's and two B's. But when we look at the elements here, we have A, B, C, D. Only that we have two C's and two B's. So it's the same as A, B, C, D. So the duplicate is not important. Here the set S have only one A, one B, one C, one D. Here also, it has the same A, B, C, D, but it have two B's and two C, then one A, one D. So what we're trying to say here again is that the very simple concept here, a set, the order of the element is not important, and also a duplicate is not important. So a set S with element A, B, C, D is the same as with element A, B, C, B, C, D, or A, B, C, C, D, as far as, again, the uniqueness of all the elements here is A, B, C, D, and here also is A, B, C, D. So the duplicate and the order is not important. Also, sometimes we may see ellipses in our parentheses for the set. For example, here we have set S, it's A, B, C, D, up to Z. What we are saying here, or using the ellipsis, means we don't want to write all the characters A, B, C, D, E, F, G, H, up to Z. So we just see the pattern. This will lead us to show us the pattern. I have A, B, C, D, then the ellipsis, then Z, which means A, B, C, D, E, F, G, up to Z. So here we say we use the ellipsis to describe a set without listing all of the elements when the pattern is clear. So now let's see some of the roster method here. These are some few examples. We have a set of all vowels in the English alphabet. So all the vowels in the English alphabet are A, E, I, O, U. So we can say here we have a set V. And set V elements are all the vowels in English alphabet, which is A, E, I, O, U. Also, we have another set, a set of odd positive integers less than 10. So I will look at the possible odd numbers up to less than 10. So the set name is O. Then we can see that odd numbers, that's we're dealing with only positive. The question says set of all odd positive integers. So we start from 1, 3, 5, 7, 9. We can't go to 11 because here we say odd positive integers less than 10. The next is a set of all positive integers less than 100. So positive integer means both even and odd numbers. So we can have 1, 2, 3, 4, 5, 6, all the way to 99 because less than 100. But here we are using the ellipsis. because the values are too many. So 1, 2, 3 up to 99, which means 1, 2, 3, 4, 5, all the values, integer values from 1 to less than 100. So we will go up to 99. Here also we have a set of 4 integers less than 0. Here they didn't tell us only positive. So negative values also is possible. If it's less than 0, then we start from -1 and start to reduce it. And remember here, we say all the integers values. So it will go -1, -2, -3, -4, all the way to -infinity. So we have the ellipsis here. So these are also some important sets which we're always going to face. For example, the uppercase N is natural numbers. Natural numbers means from 0, 1, 2, 3 to positive infinity. So natural numbers are positive values from 0. We also have integers, but integers can be negative value and can be positive value and also can have 0. So here we can see we have the ellipsis, which means, let's say, negative infinity all the way to positive infinity. To the right side, we have positive ellipsis. So here we have -3, -2, -1, 0, 1, 2, 3 to infinity. And the lowest also will go to the negative infinity. So which means integer can be any value from positive, negative, including 0. But natural numbers are only from 0 to positive values. Next, we have a set of real numbers. We also have a set of positive real numbers, a set of complex numbers. Complex numbers normally is a number that consists of the real part and also the imaginary part. Then we have a set of rational numbers. Again, we will see example of all these. So now here we say to specify the property or properties that all members must satisfy. So here we have a set uppercase S. We said uppercase S have element. And this element, this is another way of writing, actually we call this the set builder notation. This is another way of writing the element. So instead of writing, you see S is a positive integer less than 100. So instead of writing 1, 2, 3, 4, 5 up to 100, I can just write this condition. So set S is lowercase x as the element, and the element is positive integer less than 100, so from 1 to 99. Then we have a set O. We say set O consists of element such that the element is an odd positive integer less than 10. Odd positive. So I'll start with 1, 3, then 7, no, sorry, 5, 7, and 9. This is odd positive. So 1, 3, 5, 7, and 9. And the odd positive integer should be less than 10. Then we also have X, and we can write it in this form. Here we say S belongs or is a member of Z positive. A condition that the element is a odd, but again, less than 10. We can also use a predicate. So here we can say we have a set uppercase S. The element X is a predicate of S. So example will be, I have a set uppercase S. The element S is a prime of it. Then we also have the positive rational numbers. We also have the interval notation. So the first notation is called the closed interval, square bracket A and B. This means we have an element that is greater than or equal to 1 and less than or equal to B. So this is a closed interval. So we can say here we are using S as our element, have values less than or equal to B, greater than or equal to A. Then next we have close interval to the A, then open interval to the B. So this is same as saying that X should be less than or equal to A because it's close interval equal. Now the other part is open interval, so it should be less than B. So which means S have a value that is greater than or equal to A and is less than B. Same thing, we can see this time the square bracket is at the B section. So the equal sign will go to the B. So here we can say X is greater than A and less than or equal to B. And next section we have both open interval A and B. So S is greater than A and also less than B. So again, the symbols are here. The square bracket is called the close interval, and the open interval is regular parentheses. So next we talk about universal set and empty set. So universal set will be a set that contains everything that we are considering at that very moment. Then empty set is a set that doesn't have anything. So universal set, a set that consists of everything at a very particular time. Then empty set is a set that have nothing. So here we say universal set U is a set containing everything currently under consideration. So sometimes it can be implicit, and most of the time it's explicitly stated. The content also depends on the context. And here we say the empty set is a set with no element, symbolized as 0 dash. Or we can use an empty parenthesis. So next we have the Russell's paradox, where we say let S be the set of all sets which are not members of themselves. So a paradox will result from trying to answer the question, is A a member of itself? Now we have a condition like that, let uppercase S be a set of all sets which are not members of themselves. Now our question is that, is S set a member of itself? So this is again Russell's paradox. And another one related paradox, we say Henry is a barber who shaves all people who do not shave themselves. So a paradox results from trying to answer the question, does Henry shave himself? If Henry is a barber who shaves all people who do not shave themselves, if Henry doesn't shave himself, then that means maybe another person will shave it, or again, this is just a paradox. Now, some things to remember. We know set can be element of sets. So here we can see that we have a set that have 3 elements of set. So we have 1, 2, 3. The reason why we call this set because it's in the curly brace. Then we may have a set A, then BC. So this is set that can be element of a set. Or we have NZQR. Remember, N also is a set. Then we have the Z, real numbers, then R, rational, etc. So the empty set always is different from a set containing empty set. So the symbol here saying that we see empty set is not equal to set with an empty. We also have the set equality. We said that if we have 2 sets and the sets are equal, how do we determine if 2 sets are equal? It means if the elements in both sets are the same, then the sets are equal. So 2 sets are equal if the elements in both sets are the same. And you will say if only if they have the same element. Therefore, if A and B are sets, then A and B are, here we say, therefore if A and B are sets, then A and B are equal only if both of them have the same element. So we say all X, S belongs to A, and also S belongs to B. So again, set equality would depend on the element in each set. If two sets have the same element and the same data type, the same quantity, then we can say the two sets are equal. Here we can write A equal to B, only if A and B are equal sets. So 135 is the same as 351. Remember we said again, the order is not important. Also, duplicate is not important. So we have 1555, 331 is the same as 135. Next, we talk about a subset. A set A is a subset of B if and only if every element of A is also an element of B. So if we say A is a subset of B, it means all the elements in set A is also in B, including other items. So that's why it's a subset. So this is the notation more like a C with a slash. The notation uppercase A, C with a trash, and B is used to indicate that A again is a subset of the set B. So set A is a subset of B if and only if every element of A is also an element of B. And we consider this example, oh, since A is a subset of B, it means all the elements in A is also in B, but some element in B will not be in A. So showing a set is or is not a subset of another set. So here we're going to show that A is a subset of B. To show that A is a subset of B, we show that if S belongs to A, then S also belongs to B. Because again, A is a subset of B. Now showing that A is not a subset of B, you say to show that A is not a subset of B, find an element S belongs to A with S not belongs to B. Such an X is a counterexample to the claim that S belongs to A. So the set of all computer science majors at your school is a subset of students at your school. Because in a school, we may have more than one department, let's say business department and computer science. So both will be total students. The school have only two departments. But we can also say that the set, and the first set can be the subset of the second one if all the elements in the first one is also in the second one. So that's the example here. We have computer science major and we have other majors. They are all students in a school. So we can take only one department, which is computer science. So we can say that the set of all computer science majors at your school is a subset of all students at your school. Because the computer science major, they are students. Another example, a set of integers with squares less than 100 is not a subset of integers of non-negative integers. So let's see another look at equality of a set. Again, previously we said the equality of a set depends on the element. If we have two or more sets and their elements are the same, without considering the duplication, the reordering of the items. If they are all the same, then we say there's equality between the two sets. So here they say we should record that two sets A and B are equal, denoted by A equal to B, if only all X, S belongs to A, and also S belongs to B. Now, using logical equivalency, we have that A equal to B if all x belongs to A, and x belongs to B, and also x belongs to B, and x belongs to A. So this is equivalent of saying that A is a subset of B, or B is a subset of A. And we can use the concept of Venn diagram to explain the subset. So here we can look at the Venn diagram here, and we can say that the set A and B is a subset of U, or set A is a subset of set B. Then next we talk about the set cardinality. And the definition here said that if there are exactly n distinct elements means there's no repetition, no duplicate. So if there are exactly n distinct elements in S, where the lowercase n is a non-negative integer, we say that S is finity. Otherwise, it is infinity. So again, if there are exactly n distinct elements in S, where n is a non-negative integer, we can say that S is finity. Otherwise, it will be infinity. So here we say the cardinality of finity set, which normally denoted by absolute uppercase A, is the number of distinct elements of A. So example here, we can see the first is correct, 0. Let S be the letters of English alphabet, then S 26, because we have again 26 alphabet letters. Now if I have 1, 2, 3, parentheses is 3, 0 is 1. We also have what we call the power set. So a power set is a set of all subsets of set A, denoted by P at A, power set. So example, if A have element lowercase a and B, then power set of A will be 0, AB, and also another AB together. And here also we said that if a set has n elements, then the cardinality of the power set is 2 to the power n. We may study this more in chapter 5 and 6, or unit 5 and 6 of our course textbook. So next we go to what is a tuple. Tuples is used a lot, even the terminology is used a lot in database system. So in database system, a tuple is a record. A tuple is a record. So if a school have 200 students, and they have the 200 students in their database system, one student is one record. Also, it's a tuple. So a tuple is an ordered n tuple. Is the order collection that has A1 as its first element, A2 as its second element, and so on to AN. So two n tuples are equal if and only if their corresponding elements are the same or equal. Also, the ordered pair A, B, C, D are equal if and only if A equal to C and also B equal to D. And our last section is Cartesian product. So the definition of a Cartesian product is if we have two sets A and B, we can donate it by A times B, and it will be the set of order pairs of AB where A belongs to uppercase, A belongs to uppercase, lowercase a belongs to uppercase A, and lowercase b belongs to uppercase B. So Cartesian product, what we're trying to say, if I have A times B or A times A Cartesian product B, It means I'm going to multiply all the elements in each set together. So we start with the left one can be row, the other one will be column. So if I have set A and B, and let's set B have 1, 2, 3. So the element of set A is lowercase ab, the element of set B is 1, 2, 3. Now I want to find the Cartesian product of both. So what I'll do, I'll multiply A by 1, 2, 3, B by 1, 2, 3. So we can see A times 1, A1, A times 2, A2, A times 3 will be A and 3. Then B will be B1, B2, B3. So the definition will be a subset R of the Cartesian product A by B is called a relation from the set A to the set B. And relations will be covered in depth in chapter 9 or unit 9 of our course textbook. So the definition again, the Cartesian product of set A1, A2 up to AN, donated by, again, A1 by A2 all the way to AN, is a subset of order n tuples. And why we say n tuples? Because we go from A1 to AN. And it's A lowercase A1, A2, then AN. Where we say that AJ belongs to uppercase AJ for I equal to 1 to N. So example is given here, A times B times C. We have a set, 3 sets. A is 0, 1, B is 1, 2, and C is 0, 1, 2. So what we do is that we take the first set, multiply by second, then multiply by the third. So we can see how it looks now. We start with, how do we get 0, 1, 0? I take the first set, 0 times 1 times 0. Then second test, 1 times 1 times 0. And what we do is that we're going to multiply each element by itself by the following, the other set elements. So 0, 1, 1, 2 will be 0 times 1, then 0 and 2. Then we take 1, 1 times 1, 1 times 2. We add it together. Then we get the result. So this will be the conclusion of our lectures on the basic concept of sets. So in this lecture, we learned about the concept of a set, the set theory, definition, and some few properties, empty set, universal set. So we also can have a set element as a predicate. So we say, given a predicate P and a domain D, we define the true set of P to be the set of elements in D, for which P at S is true. So this means the true set of P at S is denoted by S belongs to D, giving predicate P at X. So an example here will be the true set of P at S, where again the domain is the integer, and P at S will be the element from 1. So the set is -1 to +1. So again, this will be the conclusion of our lectures on the basic concept of set. And see you in the next lectures. Thank you.